Welcome to Shanti-Peace for Mathematics. In this video, we'll give some introduction about the infinite series. Infinite series is frequently appear in many engineering problems, physical problems and chemistry problems. And therefore, it is very necessary to understand the convergence and the divergence criteria for it. Particularly in mathematics, the study of infinite series is very important in order to determine the value of many functions. Also, for this purpose, it is extremely used in calculators and a computer. So, the infinite series is defined as a sum of infinite sequence. So, if you have u1, u2 up to un and so on is an infinite sequence of real numbers, then the expression of the form, that is u1 plus u2 plus u3 up to so on, un and so on, it's called an infinite series. It's just also known as a series, and it is denoted by summation of n running from 1 to infinity un or just summation un. To understand the convergence and the divergence of the series, we should understand what you mean by a sum of first n term. It is also known as a partial sum. So the sum of first n terms is denoted by Sn. That is, Sn is equal to u1 plus u2 plus up to un. So it is a sum of first n term is there. And if this expression, that is u1 plus u2 plus un up to so on, is called, it is a finite terms, it is appear there, then it is called finite series. Whenever you have a series, it is interesting to know whether this series is convergent series, it is divergent series, or it is oscillating series. I can say a classification of the series in the three types: convergent series, divergent series, and oscillating series. Let us discuss them one by one. So the first one that we are discussing, it is a convergent series. A series summation of un is said to be convergent if Sn, that is a sequence. So I can say a sequence, the sequence of partial sum Sn is converged to a finite and unique number s. That means if the limit of Sn as n tends to infinity is s, then s, it's called the sum of the series. Let us look at this definition and see this one. We have a sequence. Sn is defined like this. Sn is u1 plus u2 plus up to so un. So it is a partial sum we have. Let us see some terms of this sequence. So S1 is the first term u1, that is the sum of first term. S2 is the sum of first two term, that is u1 plus u2. S3 is sum of three terms, that is u1 plus u2 plus u3. And so on. Sn is the sum of nth term, first n terms, that is u1 plus u2 plus un. So this I can write down as summation k running from 1 to n uk. And so what we can observe here, this Sn is a sequence of real numbers. And if this limit of this Sn, that is as n tends to infinity, that means a limit of this summation k running from 1 to n uk is exist, and if it is a unique finite number s, then we can say that a series un is convergent. So that is a definition of the convergent series. So I can say a definition in short: a series is convergent if its partial sum is convergent, or a sequence of partial sum is convergent. Now the next definition is the divergent series. So a series summation of un is said to be divergent if the sequence of partial sum that is Sn, it's tend to infinitive or minus infinity as n tends to infinity. That is a limit of Sn is plus or minus infinitive, either plus infinitive or minus infinitive as n tends to infinitive. If it is there, then it is called the divergence series. A next definition, or I can say a classification, is the oscillating or oscillatory series. A series summation of un is said to be oscillatory series if the sequence of partial sum Sn is neither tends to a finite number, finite unique number, nor plus infinitive or minus infinitive as n tends to infinity. So that is the definition of oscillatory series. So that sequence of partial sum, if it is not convergent or not divergent, such series it's called the oscillatory series. So if the value of Sn as n tends to infinitive is fluctuate between the finite range, then that series is said to be oscillating finitely, while Sn is tending to plus infinitive or minus infinitive alternatively, then it is called oscillative infinitely. So that things I am writing here. If the value of Sn as n tends to infinity fluctuate within finite range, then the series is said to be oscillate series, oscillate finite series. While if Sn tends to plus infinitive or minus infinitive alternatively, then it's said to be oscillate infinitely. So that is the definition of oscillating finite and oscillately infinite. So a series with which diverge or oscillatory series, they are oftenly referred as non-convergent series. So the non-convergent series are referred as a divergent series or they are the oscillatory series. So here I have just told you about the non-convergent series. So non-convergence means it is either divergent, diverge or oscillate. That series are called the non-convergent series. Let us see some of the examples to test the convergence of the series. Very basic examples I am taking here. So test the convergence of the series, that is 1 upon 1 into 3 plus 1 upon 3 into 5 plus 1 upon 5 into 7 up to so on 1 upon 2n minus 1 2n plus 1 up to so on. So this is the series of this form is given. We need to see whether this series is convergent or divergent. We need to test what it will be. This series is convergent, divergent or oscillating series. So for that I need to understand what is the partial sum. So here what is Sn is given. The Sn is 1 upon 1 into 3 plus 1 upon 3 into 5 up to so on. This is 1 upon 2n minus 1 into 2n plus 1. Now we just observe what we will do here. In this term I am just multiplying and dividing by 2 here. And so what we are doing is we are just doing this 3 minus 1 upon 1 into 3. So what is the 3 minus 1 will gives me 2, so that is 1 by 2 I am multiplying here. The same thing I am taking in the denominator, we will have 3 into 5, so I just write 5 and 3 and in between minus sign. So the left answer is 2 and 2 already have divide here, so we multiply that. Same thing we will do for this thing in each term. In the last term also we are doing the same thing, that is 2n minus 1, 2n plus 1 we have here. So we will just write this 2n plus 1 minus 2n minus 1. You just observe that what is the left here, this 2n will get cancelled out 1, this is minus minus become plus 1, so it will become 2 and 2 we already have multiplied. So this will gives me, if I partial factor of this one, that this will gives me 1 upon 1 minus 1 upon 3. This is the first term of this we get. Plus here we get 1 upon 3 minus 1 upon 5. And so on. Here we'll get it is 1 upon 2n minus 1 minus 1 upon 2n plus 1. And you just observe what we will get here. This 3 will get minus 3 and this 1 by 3 is cancelled out. This 1 by 5 is cancelled out with the next term to that, and this 1 upon 2n minus 1 is cancelled with this previous term. So what is the left quantity is here? It is 1 minus 1 upon 2n plus 1. So therefore this Sn will lives with 1 by 2 into 1 minus 1 upon 2n plus 1. And if I take the limit now as n tends to infinity, will gives me 1 by 2, a limit of n tends to infinity as 1 by 2 is independent of n. We'll write this as 1 minus 1 upon 2n plus 1. And if you take the limit n tends to infinity, 1 upon 2n plus 1 tends to 0. So that quantity will lives with 1 by 2. So hence the limit of this Sn is 1 by 2, and which is a finite quantity and it is a unique. So thus what we can say, the series is convergent and its sum, actually the sum also we can have from this is 1 by 2. The sum will be 1 by 2. That means this, the sum of all the series that we have here, the sum is here, it is 1 by 2 we can obtain. Similar kind of examples I can give you here as a homework, that is known as a telescoping series. This series is known as a telescoping series. The test the convergence of series summation n running from 1 to infinity 1 upon n into n plus 1. So it is a similar kind of examples as we have discussed in the previous one, that is 1 upon 1 into 2 plus 1 upon 2 into 3 up to so on. This is 1 upon n into n plus 1 and this sum goes to infinity. So I will suggest that you can solve this example by yourself. And why it is called, this type of series is known as a telescoping series. Why it is known as a telescoping series, I will tell you a result for that. You just see the partial sum of that. So that means if I have a telescope from this side, if I put telescope here, then I can see from the first term to the last term. So that's why it is known as a telescoping series. So it works as a telescope. I can see from first term to the directly last term. So that's why this type of series is known as a telescoping series. Let us have a next example. Is the convergence of the series 1 plus 3 plus 5 up to so on. So it is a sum of all odd term we will have. So to know this, and it is a arithmetic progression we have, and it is a difference of that arithmetic progression is 2, but it is infinite arithmetic progression, not finite one. So to see this one, we need to see what is here Sn, that is the partial sum. The Sn is 1 plus 3 plus 5 up to the nth term we will have. This is the first n term we'll have 2n minus 1, and this is what we have. It is a arithmetic progression with the difference is 2. So we know that if it is a arithmetic progression is of the form a plus d, a plus 2d up to so on, a plus n minus 1d, and the sum of this one is n by 2 into 2a plus n minus 1d. So as per this one, this will be n by 2, that is the nth term is there, 2a, the a is the first term we have, here it is first term is 1, plus n minus 1d, d is the difference of two terms, here d is 2. So that's why this will gives you n by 2, 2a, that is 2 into 1 plus n minus 1 into d, that is 2. And if you simplify this, then it will left to n by 2, 2 plus 2n minus 2, so that will left with n square. So the sum of this Sn is n square, and that will gives me therefore limit of Sn as n tends to infinity is limit of n square as n tends to infinity will be infinity. So thus what we can say, the given series is divergent. So from this we can say it is a divergent series and it is diverged to infinity. Let us have one more example. Take the convergence of the series 1 minus 1 plus 1 minus 1 plus 1 and so on. So it is the alternating series. If you can see that alternating series, what will be the Sn? Here the Sn. But what is happening? If I take the even terms of this, then so if I take the even terms, that is S2n will be 0, and if I take S2n plus 1, it will be 1. You can see that if I take first 2 terms, then answer is 0, 3 terms, then answer is 1, 4 terms, then answer is 0, 5th term, if I add, then answer is 1. So whenever we have even terms, it has answer 0. When we have odd terms of this sequence Sn, it will have answer 1. So that means the limit is fluctuating between two things. That means the limit of Sn as n tends to infinity is either 0 or it will be 1, which is a finite quantity, but it is not unique. So we can say limit, therefore the limit of Sn n tends to infinity is fluctuate within finite range, and therefore the series is oscillatory series, oscillates finitely. This is the things we got from here. Let's solve one more example. Question is again, take the convergence of summation n running from 1 to infinity tan inverse of 1 upon n square plus n plus 1. See whether this series is convergent or divergent. Here let us observe what we can have here. Here we have given tan inverse of 1 upon n square plus n plus 1. You just see in the numerator it is 1, so I'll just adjust that 1 with the n plus 1 minus n upon n square plus n plus 1. If I divide this quantity in the numerator and the denominator by n into n plus 1, then what we will get here, so I'll divide in the numerator as well as in the denominator with this quantity. Here this is the first term we'll have, n plus 1 divided by n into n plus 1 will gives me 1 upon n, minus n divides by n into n plus 1 will gives me 1 upon n plus 1 upon, this is n square plus n. So that will gives me 1 plus, because n square plus n is exactly this term. So it is 1 plus 1 upon n into n plus 1. So as you know, this is the formula for tan inverse of x minus y upon x 1 plus xy. So using that formula, that is tan inverse of x minus y upon 1 plus xy will be tan inverse of x minus tan inverse of y. That we know. So hence what we get, it is tan inverse of 1 upon n square plus n plus 1. As per this, we can have it as tan inverse of 1 by n minus tan inverse of 1 upon n plus 1. So now what will be the Sn we have? Sn is summation k running from 1 to n tan inverse of, that is, this is my term, that is tan inverse of 1 upon k square plus k plus 1. And if you substitute this value here, so therefore Sn is this summation k running from 1 to n tan inverse of 1 by k minus tan inverse of 1 by k plus 1. And if you expand this summation, by putting the value, we'll have tan inverse of 1, that is k is 1, minus tan inverse of 2. If I put k equal to 1 here, this is the first term, plus tan inverse of 1 by 2 here, tan inverse of 1 by 2 minus tan inverse of 1 by 3. If I put k equal to 2 here, we'll get this tan inverse of 1 by 3 minus tan inverse of 1 by 4 up to so on. The last term will have tan inverse of 1 by n minus tan inverse of 1 by 1 plus n. And you just observe this, tan inverse of 1 by 2 is get cancelled out, tan inverse of 1 by 3 will get cancelled, 1 by 4 is cancelled with this next term, 1 by tan inverse of 1 by n is cancelled with its previous term. So only two terms is left, that is tan inverse of 1 minus tan inverse of 1 upon n plus 1. And if I take limit now as n tends to infinity, so the limit of Sn as n tends to infinity will gives me a limit of n tends to infinity tan inverse of 1 minus tan inverse of 1 upon n plus 1 will leads to tan inverse of 1 will leads to pi by 4 minus tan inverse of 0 we can have, because tan inverse of 1 upon n, tan inverse is a continuous function, so 1 upon n as n tends to infinity tends to 0, and tan inverse of 0 we know it is 0, so the answer is pi by 4. So hence it is a finite quantity and it is unique. So thus what we can say, the given series convergent and the sum of that series is pi by 4. That's it for this video. If you like this video, please press the like button. If you have any comments, suggestion or a question, please drop down in a comment box below. See you in next video. Till then, bye bye, sayonara.